Now let us have a difficult example which has lots of good applications. And this example in statistics we call it order statistics, and in computer we call it sorting. So suppose that you have a set of random variables or a random vector as input, and then you sort them. If you sort them, sometimes x1 is the largest, will go as your first entry at the output, and sometimes xn is the smallest goes at the end. But if you have these sorted values, you don't know which one was the largest. So the set of possible solution could be any permutation of the output. So basically, if you know the sorted values, what are the possible set of solutions for the input? So answering this question is the main trick to solve this one. So basically here we assume that we know the joint density of the input of this sorting machine, and let's say y is the output, and we want to find the joint density of the sorted values. How we do that? So for any problem like that, we have to see if we know the output values, we have to solve these problem. What are the possible set of values for the input? And here is the input of the sorting machine. So order statistic. Definition is that if you have a set of random variables, let's say x1 to xn, and then you sort them, so you don't know which one is going to be the largest, which is going to be the smallest, and so on. So we may denote y equal to sort of x, and then you lose information, because if you have x, you can find y, but if you know y, you don't know which one was the largest, which one was the smallest one, and so on. So, so this equation, y equal sort x, has n factorial solution, because any possible permutation of the output can be one possible input. So n factorial is the number of all possible permutations. Basically, sorting is a permutation which puts the numbers in order, and because we don't know which one was the largest or smallest and so on, so all permutations are the solutions. Because if we apply any permutation, arbitrary permutation to y, okay, so if I put y and put it arbitrary permutation, and if I apply sorting to it, I will get y back. So any permutation of y is one solution. So the set of possible solution x, one solution is x equal py, when p is a permutation. And remember that p is a matrix, a permutation, and its entries are all zeros or ones. So you have in each row, you have only on each row you have only one. For instance, here you could have 0, 0, 0, 1. So if you have 1 here, then everything else is 0. On this column and on this row, you have only exactly one. Everything else is 0. On let's say on the second element, you could choose, let's say, this one to be 1. So everything else becomes 0, and here you have 0. So in total, you have n ones, and rest of remainder of entries of p are 0. So this is a permutation. Permutation, when you multiply p by y, just you change the order of entries of p. So so this is a permutation, and you can easily see that f y of y is equal to summation over all permutation, all possible p's, and then how many of them we have, n factorial is going to be fx of p y, okay, and then divided by Jacobian. Here is Jacobian is equal to 0. But the point here is that here y1 is smaller than y2 is smaller than yn, okay, and the PDF is 0 wherever this condition elsewhere. Wherever this condition is not valid. So it is easy to calculate the PDF of the sorted value, just you apply all the permutations. For example, suppose that you have a set of IID means they have identical distribution, and the second I means independent. Identical and independent distribution. That means that their distribution is identical and their distributions are independent. So if I say this one, f x of x is basically product of I equal 1 to n, and then f xi of, let's say, xi. So this is the meaning of this one. So if it says identical distribution, that means that this distribution here, it doesn't depend on I, so you could remove this I. So this function is same for all of them. So in this case, we have seen in the previous chapters that the distribution of, let's say, k, the kth order statistic is equal to that, because out of n, k of them should be smaller than y, and n minus k should be bigger than that. And from here you can get this one. So if yk is probability that k out of n random variables are less than this, and this is a Bernoulli experiment. So it's kind of like you say, because these y1, yk, etc. are sorted, so we know that this is below that. So if yk, we want to find that, so all of them should be below that, and then you can argue that. Another example, consider a system consisting of m component, and let's xi denote the time to failure of the ith component of the system. So in that case, the probability that ith component is good at time t is equal to, and this is the reliability, is the complementary CDF of xi at time t. Now, you could define n as the number of components that are working at time t. So basically, this n is defined for time t. So I could have, say, ni t, but because we haven't talked about the stochastic process, I omitted these t. Suppose that we are frozen at time t. So in that case, this is just a random variable for time t. And denote the number of components that are good at time t. This is going to be, so this ni is an indicator random variable, which indicates if the ith component is working at time t or not. If it is 1, that means that it is operating at time t, and if it is not, 0. So the number of components in this system is just sum of those which are working. So you can calculate mean of ni, which is going to be equal to the reliability. So mean of nt is just the sum of reliabilities. So and when the random variable xi has the same distribution, if these distributions are equal to other, if this guy is not a function of I, so instead of this one, this will become m sub that. So simplifies to this one.